specifically when we talk about the performance of an open array, we know that there's velocity vectors that communicate between the wheels, and that velocity vector, those velocity vectors are going to change depending on how fast the wheels are spinning and how close they are together. So when we look at most fans that are found in an array configuration, they're typically going to be AMCA sound and air certified. And what that means is each one of those individual fans were put on a chamber and tested, similar to what I'm showing you on the screen here. And then what we assume is that if there's a 4-fan array, you just take the performance from each individual fan, multiply it by 4, and that gives you your performance for the fan array. Well, what we wanted to understand was if that is truly the case. AMCA does not have a fan array certification at this point in time. So there's a lot of assumptions made around the communication of those wheels that we just talked about. And so GREDEC really wanted to set out to understand that a little bit better. AMCA says essentially if you put one wheel diameter in between fans, there's assumed to be no performance losses, so no system effect takes place. And you would expect you'd expect your performance to be a multiple of each individual fan selection. So we set out to really understand this in much more depth. We wanted to understand how the vector velocity or how the vector velocity vectors, communicate with one another based on velocity. So how fast we're spinning the fans. And then we also really wanted to understand the impact on spacing. All right, so how do we quantify this? Well, we put a test plan together. And what it amounts to is setting up a fan array and basically adjusting the fans closer and further apart in 1-inch increments horizontally and 2-inch increments vertically. And then we're going to run that whole setup in each one of those different configurations at 4 different speeds. Okay, so it amounts to about 480 different tests. And so we set out to do that, and I'm going to try to play a video for you quick to kind of illustrate the testing that we did. And so here it is. Let me see if I can get it to play for you. All right, so if you notice down here in the bottom right corner, there's a whiteboard. And so there's the date that we started this testing, back in early October of 2018. And if you watch this video just cycle, what you'll notice is that the wheels move closer together vertically and horizontally in 1-inch and 2-inch increments. And so we go through each setup over the course of time. And I'm going to speed it up a little bit just so you don't have to sit through 6 minutes of the same video, but you'll see the fans move closer together and further apart. So every one of these setups, we're going to run the fans at 4 different RPMs, collect the data, and analyze it. So you can see we're about a month into the testing right now. And we're going to jump ahead just a little bit. So now we're in November. And by the end, so this is right around Christmas time, 2018. So by the end, what we were able to do was create some formulas to actually predict the performance of these wheels based on proximity and velocity, or what RPM you're going to spin them at. So in the end, we spent about 3 months testing the fans. We ran almost 500 tests. And now what we can do is we can optimize fan performance based on the data that we collected. So we took that data and we baked it into our CAP system. So if you're familiar with our computer-aided product selection software, when you go in to make a fan array selection specifically for an MOA, we ask you for the envelope. So we ask you for the width and the height of your fan array. And so you enter your fan array width and height and your performance, and CAP spits out an optimized selection. And then you have the ability to pick the fans or the fan array that best fits your needs, whether that's based on efficiency or cost or sound or number of fans, you're able to pick the best fit for your application. So I've got an example as we talked about the communication and wheels. So these are selections that I made in our CAPS program, and these are 22-inch wheels. I picked a design point of 7,000 CFM at 3 inches of static. So to hit that performance with a 22-inch wheel, our fan RPM is 1635, and brake horsepower is 4.68. So now let's take that same wheel and put it in a fan array. All right, so my example here has 96 inches between centers. So we've got 8 feet of spacing between the wheels, so they're very far apart. And in this scenario, you can see the volume, we just multiply by 4. Static pressure remains the same. Fan RPM is not impacted. There is no system effect at this point because the wheels are far enough apart. And our brake horsepower is a factor of 4 as well. So now let's start to put those wheels a little bit closer together. So we've got 22-inch wheels at basically 1 wheel diameter apart. Again, volume remains a multiple of 4. Static pressure remains at 3 inches, but now we have to spin the wheel a little bit faster, 1.3% faster in order to hit that same performance. And you'll also notice that brake horsepower went up, and it goes up by a cube, so it's 4.3% more brake horsepower to hit that same performance point. Okay, let's take that one step further. So now we have a half a wheel diameter. Again, static pressure and volume stay the same, but now our fan RPM goes up 3.3% and brake horsepower goes up 11.1%. So there's a real life impact in putting these wheels closer together. And I don't know about all of you on the call, but I've been out in the industry looking at fan arrays, and a lot of times you see wheels or fans stacked very close to one another. So this is a half wheel diameter in between. I've seen them stacked a lot closer than that. So it's important to take into account certainly proximity and what the communication is that's taking place between the wheels. Now, in some applications where it's just a single air handler, it's probably not a huge impact. So if you don't hit your performance, you spin the wheels a little bit faster and get to the performance point that you need. But when you think about this on more of a mega scale type application where you're moving over 1 million CFM and you might have 150 motors in the application, every fraction of brake horsepower adds up, and it adds up fast. So it can be important on a larger scale.